So David, are you ready to take us to the Pareto Front?
I'm ready.
Okay, good. Oh, I can't wait. Brilliant. Okay, cool. So, David, thanks for joining us today. So, do you want to very quickly introduce yourself, David?
Yeah, so my name is David Percival. I'm a senior project engineer for EnginSoft UK. Been working with the company for around almost 3.5 years now. I'm the UK lead engineer for all Particleworks activities. So I work on client projects, software sales, training, and methods development pieces.
Fantastic. Oh, anything else? Carry on.
No, that's fine.
Cool. So who am I? For those who don't know, my name's Alex Redman. So I head up, business development, strategy. So quite a bit of sales, bit of marketing, company level strategy, but also for our respective clients in terms of simulation strategy. And I think so. At the moment, I'm also leading on CFD sort of disciplines in terms of being pulled into some meetings, but I'm not sure I'm at a comparable level to yourself. But I certainly try my little best. So what we're doing today, we're going to talk a little bit about Particleworks, and in particular, instead of shining a light on products all the time, let's talk about specific problems. So we want to frame this discussion around piston spray cooling. So obviously we've done a bit of work in that space. So we'll just have a bit of a chat about it. We can let the conversation meander where we kind of want, and hopefully we can have as many kind of examples and interesting facts and the like as we go along. So, do you want to sort of start us off, David? What is the kind of piston cooling problem? So, let's frame the problem statement.
So, well, the problem with piston cooling is that it's a very hard subject to test in reality. There's no way of making a clear case testing to see how the oil spray is distributed over the underground of the piston and within the gallery. So it's not something that we can really physically test, other than maybe making a physical prototype, running it, and then potentially doing some hardness analysis, or putting some thermocouples in the piston if you have a large enough piston, something like a marine engine potentially. What we want to do with Particleworks is actually simulate that, and this is something that we can't do with traditional CFD because we have a spray which is traditionally very difficult to simulate using a mesh-based CFD, just because of the size of the mesh elements that we require in order to capture that accurately. So this is something that's really beneficial when we don't need to use a mesh using a software package like Particleworks.
Yeah. Okay. And before, so when we sort of, let's say, engage with a client or prospect, to use sales parlance, how are they doing this what's your vibe from the market in terms of how people are struggling with this issue? Is it we're only doing hardware testing, or is it a case of it's just too difficult, engineering empirical best guess analysis? What do we do on the last program? If it ain't broke, don't fix it. What's that kind of journey to what we then propose?
Yeah, I think exactly what you said there is a best guess for the most part. Some people do some testing physically, but as you say, if it ain't broke, don't fix it. We've seen some people try with traditional CFD, and it's just not gone anywhere, just because it's not the right tool for that application.
So in terms of Particleworks, then, and we'll try and not be too salesy. I might have like a bingo thing if we think we're getting too salesy. Can you go into a bit of detail about what is the MPS method? Moving particle solution or simulation, whichever camp you want to sit in. So the sort of fundamentals of it, and then pivot that into why that means it's such a wonderful solution for something like piston cooling. So assume I know nothing, and because that's probably at a level slightly below the audience, let's say.
Okay. So the MPS method is one of only a couple of meshless CFD methodologies that are out there. The MPS method is actually the only meshless CFD methodology which is designed for incompressible fluids such as oil. the way it works is rather than solving the Navier-Stokes equation on the nodes of a mesh, which is kind of like taking the outside point of view or the Eulerian point of view of solving the equations, what we're doing instead is solving from the point of view of the particles. So the particles are created with some velocity, some fluid properties, and then we solve from their point of view. And in this way, the particles kind of act as their own mesh. And the benefit for something like a spray cooling analysis is that in traditional CFD, a mesh-based CFD, we would need to have a very fine mesh throughout the entire domain to capture that spray and that free surface at all times. And that's going to create a huge number of nodes that we have to solve on and a massive computational cost. So it's just not feasible to simulate in a reasonable timescale. But for Particleworks, as we're only solving where the fluid is, or the MPS method, I should say, because we're only solving where the fluid actually is, we're not wasting that computational time in regions where we're not interested. So any application where we have a free surface or splashing, then Particleworks or the MPS method is perfectly suited because of that lack of a mesh. So we can really capture that surface resolution accurately at all times.
Yeah, okay, understood. So if I try and use, let's say, my layman's terminology, what we're essentially saying is with traditional CFD tools, when we say meshing, we're saying discretization, and when we mean that, because arguably that's even less of a layman's term, we're basically saying for whatever thing we're studying in the engine, the underside of a piston in the bore together, with the crank, we've got to cut that up into loads of little squares, and we have to do that in a clever way of refinement, so that we properly simulate the, let's say, splashing that might result from those kind of oil jets. And what you're saying is, if you use Particleworks, because that meshing is on the actual oil itself, because we're modeling it as basically loads of tiny little balls. For some reason, I have some juggling balls here. But when I'm stressed on calls, that was a very hard. I didn't even plan that. It was a very hard. What else have I got here to use? It means that simulation setup time is so much quicker and easier, isn't it? Because we haven't got to do that meshing step, that discretization, that cutting it up to simulate and allow us to define that action mathematically, let's say. But it also means that we don't have to guess where the fluid is going to go before we've done the simulation, because the mesh is moving as the particles are moving, as the fluid is moving. So it's let's say a much, I would argue, a cleverer way of modelling those specific challenges. So to play devil's advocate here, then, David, where is something like Particleworks not good for in an engine? So one thing I always like to think about on these kind of topics is there's a quick fire way to lose credibility in any discussion, which is to be all things to all men and promise everything. Yep. But actually, if we can have a conversation and say, well, where is the tool weak?
Yep.
And where are traditional CFD tools better? So maybe if we frame that within an engine environment, so ICE, internal combustion engines, whatever your nomenclature is, what problems are we trying to simulate? So you've got things like 1D analysis, let's call it Ricardo Wave, GT Suite, where you're modeling, let's say, the base engine performance. You've got the actual, let's say, winding driven airflow. I'm probably using the wrong language. You've got bearing lubrication. You've got lots of. So what tools are the right tools for the job?
Yeah, so there's many applications where Particleworks isn't suited. As you say, you need to know what the right tool for the right job is, and there is no one tool that can solve every single problem. Within an ICE environment, the sort of applications that Particleworks isn't best suited to is kind of any internal flow where the flow is saturated. So if you've got like a oil recirculation network, for example, we can simulate that within Particleworks, but in reality, you're probably going to benefit from using a traditional solver or a 1D analysis instead, because we know where the fluid is going to be. We don't need to worry about a free surface because there isn't a free surface. So we can very quickly and easily make a mesh throughout a pipe. And arguably, it's not the right tool either, because we are limited, or at least in the current versions of Particleworks, we are limited to a single particle size. So for something like an internal flow, we're quite interested in what's happening close to the surface, so happening on the pipe surface. So in traditional CFD, we would usually refine the mesh in that region and have a more accurate representation close to the pipe. But within Particleworks, we can't do that, so we are stuck to a single particle size. For the same reason, slightly changing topic, for things like aerodynamic analysis, Particleworks again is not the right application, because where we get the majority of the contribution to the drag is on the boundary layer around the vehicle, or around the plane, or whatever you're simulating and analyzing. So in that region, we would create a very fine mesh to accurately calculate that drag. But in Particleworks, we're stuck to that one particle size. So where we would normally have a very coarse mesh very far away because we don't really care what's going on, we are stuck to the same particle size throughout the entire domain, and we're going to either massively increase the computational cost by having a small particle size everywhere, or have a very inaccurate simulation because we're not capturing that boundary layer prediction accurately.
Okay, and so bringing it back into specifically engines then. So we've mentioned about, let's say those oil circuits. I think you mentioned it's probably not the right tool because it fails those two tests, and it. So what do we normally say? Is it an incompressible fluid, an oil or water? If it isn't, maybe a traditional tool is better. And is there a free surface? So it's incompressible fluid in that case. But it doesn't have the free surface, so maybe it's not the right tools. You would quite easily check. So what about things like, the air movement within the engine, driven by the cranking motion? Is it the right tool for that? And do we need to consider that for piston cooling?
So Particleworks, in terms of the MPS tool, probably isn't the right tool for airflow within the engine. It's definitely not on the combustion side of a piston, just because we cannot simulate compressible fluids within Particleworks. So that simply cannot be done, actually simulating that compression. Around the rest of the engine, we could use it, but again, there's not a free surface involved, so using the MPS method probably isn't the most appropriate. That said, however, Particleworks does now have an FVM solver, which is a finite volume method solver, which is kind of like the bridge between traditional CFD and Particleworks. So rather than having to generate a mesh ourselves, it just generates a Cartesian mesh throughout the entire domain. So equally spaced grid throughout all free space within the domain, and we can solve for the airflow on that. Now, where that becomes weaker again is the fact that we can't refine that mesh. So if we are looking at trying to get really accurate prediction around a certain component, well, we can't really do that in Particleworks, as we have a fixed mesh throughout the entire domain. So anywhere where you want really accurate resolution around a specific component, yeah, you'd need to use a traditional solver for that application.
Yeah. Okay. All right. And there's obviously things like oil misting. I mean, I'm probably listing topics for other podcasts, so I'm shooting us all in the foot here. So maybe we'll come back to some of that stuff. So there's obviously other tools for piston cooling. So why would I use Particleworks over another tool? So here's. Do I mention them? I don't even know what the rules are on this, but let's be open and honest. Siemens has got a version. I think it's an SPH tool. I think it was Nextflow that they bought, based in France, in Nantes. Am I pronouncing that right? Nantes. I have no idea, how uncouth of me. What we also got, you've got Altair Nanofluid X. So just being open and honest, those products are there, and there's a whole raft of others. Certainly, my reflection, looking at the market, is a lot of providers are moving into this space. My reflection is a lot of the big boys, with their clever tokenized business models, where they kind of gaslight clients into thinking that it's within the product family, therefore it's free. Once you've negotiated it. Just looking at their sort of marketing content, they're all heavily trying to push this. Do you think that's because they recognise the threat of Particleworks? They realise that it is a superior product in the market. They realise they need to cover it off so they can have their products as sticky as possible with their customers. What's your view on the sort of competitor landscape, and then focusing on specifically around the kind of piston cooling challenge?
Yeah, so what you've described there is SPH, so it's the smooth particle hydrodynamics method. the reason why Particleworks is a major competitor to that methodology in the space of piston cooling, well, it's twofold. There's first of all, the smooth particle hydrodynamics method was originally developed for compressible fluids, and then they've made adaptations over the years to allow it to simulate incompressible fluids such as oil. But in order to satisfy the stability conditions which are inherent to the SPH method, we require a much smaller time step than we do using the MPS method. So a smaller time step means that we need to perform more calculations, and that means the simulation takes longer to run, which is often the reason why often these tools suggest running on multiple GPUs, whereas Particleworks suggests running on a single GPU, which obviously is a massive cost saving.
So for those who don't know, how much the GPUs cost, David?
Well, the GPU that we recommend running on, the NVIDIA V100, is around the £10,000 benchmark, around the £10,000 mark. So if you're running on a single GPU within Particleworks, 10 grand, but I've heard some of these other SPH tools recommending running up to on 8 at a time. So it's an increase of £70,000 per simulation. Well, per individual simulation if we're running one at a time.
I'll pay you £5 later for getting that little trinket dropped in there, but I think I need to press the bingo buzzer on being too salesy. So maybe need like a whistle or something. I don't know.
The second point of why the MPS method is more beneficial than SPH is that many SPH tools can't calculate what we call the heat transfer coefficient.
Right.
And instead they do a conjugate heat transfer analysis. So they actually simulate the change in temperature in the solids and in the fluids. And that's fine. The problem is that the stabilization timescale of thermal simulations is much longer than fluids. So for a piston cooling simulation, we're probably going to have a steady state fluid flow definitely within a second. If there's a large gallery, it may take a little bit longer to fill a steady state. But if it's just an underground spray, it'll probably be within a couple of cycles of the engine. But to actually simulate the full thermal equilibrium, that's going to take minutes, which obviously is going to take a lot longer to run that simulation. As in Particleworks, we can take that steady state fluid flow and go into what we call we take that as a boundary condition for a finite element analysis to solve for the thermal analysis in steady state, which is much faster. It means we can iterate through our designs in far shorter timescales than we ever could with an SPH tool that can't calculate the heat transfer coefficient.
Yeah, absolutely. Okay, cool. So yeah, I mean, you're throwing in the kind of key things there, which is fundamentally with some of the methodologies that we've developed in partnership with our partners and customers. Here's your hook, Cameron, when you're editing this later, so we can do it faster. Because we can run a lot faster, it means we can iterate more, which means you're going to get a better design out that's more optimized to functional performance. And arguably, if we can do it in less time, either from using less solving, compute resource, or just fundamentally less man hours, or because you're releasing right first time, so you're going to have less testing phases. You might be able to remove testing phases. You can do it cheaper, faster, better, cheaper. There, got it in. That's massively hit the
yeah, get the whistle out.
The sales bingo buzzer there. So I'll wind it in. So David, let's take this topic onto, let's say, some client-specific case studies that we can talk about. So you've obviously been involved with this topic for a number of years. If you look around the industry, who do you think is doing really well on this topic for who we can talk about? Is there a case study people can go and have a look at? What do you think good looks like? And how do you think we can take this topic to the next level?
Interesting. Who can I talk about? So I know we do have a very nice case study from Wärtsilä. I mentioned earlier about marine engines being great because we can stick as many thermocouples as we like in them.
Why is that, David?
Just because they're so large, you can almost walk around inside the gallery of some of their pistons. So we have a very nice case study where they stuck best part of 20 thermocouples in the piston, performed physical tests on a number of different loads. We simulated the same loads within Particleworks and found near perfect correlation between simulation and measured temperatures. Again, they were using the methodology that we talked about, where we're calculating the heat transfer coefficient and then going into an FEA solver to increase efficiency. Yes, who else can I talk about? We've got some case studies from Ducati, who were specifically looking at improving the spread of oil. So not so much focusing on the actual thermal aspects. They were just taking the assumption that if we increase the spread of the oil on the undercrown, then we're going to have a improved cooling rate. And they actually tried to optimize it by improving the spread while reducing the flow rate, so we can lose less power through the oil pump, and overall run with less oil, so we've got less mass in the engine. On a similar topic,
so that helps from like a downsizing point of view, not just
absolutely, yeah.
engine liter downsizing, but actually the components within the engine to further enable, in the spirit of downsizing, not just the engine itself, but the components within and on the engine.
Exactly, yeah.
Okay, carry on. Sorry, I rudely interrupted. You were in flow. There we go. Flow, free surface flow. I'm here all week. Wow. I'm here all week.
Yeah, so on a similar topic to that, we actually have a true optimization case study that I ran with Royal Enfield a couple of years ago, and where we coupled Particleworks to our optimization software Mode Frontier, and allowed Mode Frontier to modify our simulation. Just a couple of parameters that were completely free and had no effect over the rest of the design. So I think it was the position and rotation of the spray nozzle, and then the diameter of the drilling within that nozzle, which thusly affected the flow rate that came through it. So we were overall trying to increase the spread of oil, as well as increasing the total average HTC over the undercrown. But we had a constraint that we didn't want to over lubricate the pistons. There were some drainage holes within the piston, and we didn't want to allow more than 5%, I believe it was, of the total flow rate through those holes, because this would create too much oil within the cylinder, which would over lubricate and potentially allow for oil to get into the combustion changer, which would increase emissions. So yeah, this was really successful, and overall we managed to increase the spread and the average HTC by, I don't remember the exact numbers, but several percent, which may sound small, but any incremental increase, especially since we're not actually changing any design, not changing the piston at all, is massive. We could take this further and also create a parameterized piston head, and allow Mode Frontier to also optimize that, which we have connected in different case studies in the past, and allow Mode Frontier to fully optimize both the design and the spray to really have a truly optimized design.
Yeah, absolutely. So what do you think? So you touched on it there, but what's the kind of next level? Where do you see the industry going? What would, if you were doing this topic and client came to you and said, David, design me the best possible piston cooling CAE program. I'm going to give you a bit of freeway on your materials mix, a bit of freeway, easy for me to say, on your manufacturing techniques. What does good look like for you?
Personally, I think Mode Frontier is the way forward. So it's a fantastic tool that can connect any number of different simulation packages together. And what we can do with this is we can connect. We can, first of all, as I mentioned there, allow Mode Frontier to optimize the design of the piston, which can then update our Particleworks simulation. And then we can even then take it on to the next step and actually run the FEA analysis based off the heat transfer coefficient, and potentially even structural analysis on the piston to make sure that we're never going to have the piston deform over its lifetime. And I think that's the best way we can really take this forward, and it allows us to have a fantastic design and really minimal man hours, because all we have to do is set up our initial simulations, define our workflow, which can once we've done it once, we can use the same workflow again and again and just plug in different models, and click the go button, allow it to run for a period of time, and have a truly optimized design that's taken up no engineering time.
Yeah, absolutely. I totally agree. I mean, I'm bad to say that because I'm a big fan of workflow automation and process automation. I'm getting it wrong. Workflow Crikey, how many beers have I had this morning? It's only, it's only 11:15. No, I'm joking. Process automation and design optimization tools, so like Mode Frontier. So that's a handy link into creating a Pareto Front, so you can have a truly optimized design. There we go. So to throw something into the mix on this for this particular topic, I think there's a huge opportunity here around additive manufacturing, specifically in piston design. So obviously, there's huge, I would think there's huge benefits of adding, leveraging additive in piston design, much lower weight, much more optimized structural analysis, let's say vibration performance. Your engine's going to be able to rev slightly higher, lower stresses. You can then weight down the actual con rods. You can then weight down the crankshaft. Your engine will rev faster through the rev range because there's obviously less mass that has to be accelerated up and down. But from a piston cooling point of view, you're not going to be constrained by the manufacturing technique in terms of getting that optimal, let's say, thermal design output that you're targeting. So is it fair to say if you were going to match something like Particleworks with Mode Frontier and additive, you're going to be able to get to a piston design that is, I was going to say, orders of magnitude in terms of moving the functional performance envelope on according to your program targets. Is that a fair statement? Do you think if you bring those technologies together, that's what, that's where this topic is going? Yeah,
absolutely. I think it allows us to do far more than we ever could test ourselves, and think of things that we never would have thought of ourselves. And the fantastic thing about Mode Frontier, that, as we've already touched on, there's no meshing involved, so it's a very easy tool to automate. Where in the past, where we use traditional solvers, there has to be a human in the loop in order to check the quality of the mesh, maybe actually create the mesh themselves. That's not an issue with Particleworks, so it's a perfect tool to be plugged into this sort of optimization loop.
Yeah. Okay. And in terms of some of these studies that you've done in the past, David, what are we talking from a sort of simulation time point of view? Because obviously when we jump on various calls, prospects, clients, a lot of them have their own workflows baked in, maybe for other topics within an internal combustion engine, and they're kind of happy with them. It's taking X days, weeks, or whatever to run. What's the comparison between some of these load cases? Let's maybe stick with piston cooling in terms of setup, solving time, post-processing. What's the kind of delta?
Yeah, so setup, very simple. We have predefined scripts that will work for any piston to calculate the motion. So we just need to put in a couple of parameters to make it specific to your design. Once we've got the motion is by far and away the most complicated step of defining the model. So once we've got that, we can get our simulation up and running in less than an hour, probably, if you know what you're doing. Definitely less than half a day total from CAD to running simulation. Pre-processing is absolutely minimal. It's happened before you've finished your cup of tea, and well, the actual simulation. There you go. The actual simulation is dependent on a few things. So obviously, as I mentioned before, if you've got a gallery, it takes a little bit longer to stabilize. The case study that I mentioned before about Royal Enfield, which is unfortunately our only optimization case study in the public domain that we can share, that fortunately didn't have a gallery. So initially, when we ran this simulation as a standalone simulation, we ran it for, I think it was around a quarter of a second. But I performed some analysis and found out that the average HTC and the average flow rates and everything that we were measuring on that model, that I was averaging over the last 0.1 seconds, was exactly the same as the second cycle of the engine. So rather than running it for 0.25 seconds, in the optimization, I ran it for only 2 cycles, which each iteration took around 20 minutes to run. So we used to talk about days and weeks for CFD simulations, but often on these smaller scales where we have a low number of particles and we don't need to let it run for huge stabilization times, we can get to answers within minutes, not weeks anymore. Plugging that into an optimization and automation tool, I think I was able to run 500 designs in a week or something like that. I don't remember the exact numbers, but it was hundreds of designs in a very reasonable timescale.
Yeah, okay. So for specifically piston cooling as well, obviously the piston is going up and down. So how do you handle prescribing motion? Have you got to run a multi-body dynamics tool beforehand? What is the art of the possible? What do you recommend?
Yeah, so Particleworks, you have a lot of different ways you can define motion. For piston cooling or for piston motion, we have a script, or we've got a script for inline engines and a script for V engines, and we simply need to define the pin, the big end of the rod, and the center of the crankshaft, and then and then the RPM, and then Particleworks will be able to calculate the position of all three components at all times based on those three coordinates. So it's very simple to do for a piston. For more complicated things, we can run a multi-body analysis first of all. So we have options for one-way or two-way coupling with multi-body tools. I'll focus on the one-way today because I don't want to get too bogged down in the details. But for something like a chain running through oil, well, we can't prescribe the motion using mathematical equations of the chain links. So what I would suggest for that is to first run the multi-body tool, calculate the position, the rotation of each chain link individually, and then we can import that motion into Particleworks, so we can have the same motion, but it's being pre-calculated in the multi-body tool. Yeah, basically, my suggestion is wherever possible, use scripting, and that's anywhere where the motion can be defined by a mathematical expression. If that's not possible, then yeah, we'll need to run a multi-body analysis first of all.
Okay. Well, thanks for that. So I'm probably you're probably running out of puff because I'm bombarding you with questions. So we'll start maybe bringing this to a close. But it's certainly been very interesting and fascinating from my point of view. Even though we regularly have discovery calls with prospects and also existing clients to expand throughout their sort of teams globally. Every time I have a discussion with you, David, I'm learning more every day. So thank you for that. One thing I am interested in, and I hope the question hasn't just escaped my mind, is where do we see the sort of product innovation roadmap going for this kind of technology? So maybe that's a little bit out of pulling us out of piston cooling. Where do we think Prometech's going to go with Particleworks? What are some of those benefits, or maybe the other way around of saying, is it where are some of the other tools a bit stronger?
So the biggest thing that I've heard about recently from on Prometech's product development roadmap is, which is a really exciting development. The way this will work is we can define regions in which we can have refined. So if you want to have a more accurate prediction around maybe around a gear, maybe we start looking at a drag around a vehicle, and we can define a region around that object in which the will get. I'm told that this is expected in the next year or so, so I'm keeping my eye on that very closely. The FVM tool that I mentioned earlier, that's a fairly new development. I think that came out in late 2020, and that's continuously being improved and being sped up. And to start off with, it was a tool that we could only use on specific applications, but as we get faster and faster and more developed in that field, it's something that we can apply to almost all simulations to account for the airflow, where in the past we would just neglect it. So that's very exciting. Yeah, I think
putting you on the spot there, aren't I, David?
they're the main developments that I'm very excited about. There are obviously continual improvements all the time to features within the post-processing. Speed increases, so every time Particleworks is updated, there's an efficiency gain and also a scaling gain. So if we're running on multiple GPUs, there's always going to be a loss of speed. So increasing from 1 to 2 GPUs won't cut your simulation time in half. It'll probably cut it by maybe 60%, but that number's always coming down towards 50% as the scaling efficiency is improved. So yeah, there's continual improvement all the time, and it's really exciting to see where the developers are going.
Okay, I should put a little caveat on this, which is, Cameron, when you're editing this, we need to just double check we can actually share some of that information. Yeah, so if there's some random beep beep on the edit of this, that's because I've asked the question I shouldn't have asked. Anyway, that's me getting a bit geeky and into it. So my other question, David, and we will bring this to a close shortly, is just around our experiences with other customers and clients. So how do someone might approach us with a problem? Obviously, we've got existing client experiences. What's their sort of journey on piston cooling to Particleworks? Are you finding that people recognise, because of the sort of materials out there in the ether, that the product is kind of making its name for itself in this discipline, and it's much more straightforward where people say, I need this? Or actually, are people keeping their cards a bit close to their chest and saying, well, I'm within the Altair suite, I'm in the clever tokenized castle that those big players have built. I'm going to try and use this for a couple of years, and maybe they're having great results. What's your feeling from the industry and what our customers and prospects are telling us?
It's I think we're getting both, to be honest. There are some people that we go to and they have seen the value of the software. Maybe they've seen material that we've put out in the past, or they've trialed it themselves, and they just appreciate that this is the tool for these sorts of applications. And that's fantastic, because we agree with them that what we wouldn't want to sell you a tool that is not right for the job, and we honestly believe that for things like piston cooling simulation, that Particleworks is the right tool for the job. It's the best tool on the market for this specific application. However, saying that, there are also a lot of people out there which I would say unfortunately, but I don't want to sully any other competitors out there, but that they are within the Altair suite, for example, or the Siemens suite, and they are having to struggle through with what they have at their disposal. It's a challenge when we see that, because we do know that while they can probably achieve the same sorts of simulations, it's not going to be as accurate, and it's not going to be as fast as we would get within Particleworks. So what we often find is that they do need to struggle through that pain for a period of time. And many of our customers are also Altair or Siemens customers that have realized that for certain applications, it's just not the right tool. So they are using those tools which do have the correct applications. Again, like I mentioned before, there's no tool that will solve every problem. So they're using maybe NanoFluidX or one of the other SPH tools for specific applications, but then using Particleworks for things like piston cooling, where it is just so much faster and so much more accurate.
Yeah, absolutely. Okay. Just very, very quickly, have you got a metered straight after this?
I think I'm okay.
Should we carry on? Let's carry on.
Yeah, I've got half an hour.
Cool. Every time we ask you another question, it breeds another question in my mind when you start talking. So, I mean, if I can throw my sort of 10 pence, my reflection on that is, and certainly I used to, I think like this and have these pressures when I was on the OEM side. For those in the audience who know my background, I used to be at Bentley up in Crewe, and certainly we were ESI aligned, PAM crash aligned. But for some programs, we might use a different solver, but there's all kinds of challenges around that. So I totally understand the pressures when you're aligned to a certain product line. And certainly, if I was a product manager or one of the directors within Siemens or Altair, I would try and religiously protect that patch. I totally get it. But I think one of the things that we need to help educate people on, I think part of, let's say, the onboarding process for Particleworks is to kind of reinforce the fact that tokens aren't free. If you are, yes, you're getting access to a wonderful portfolio of products, and no one's going to deny that all the big players have got some fabulous tools in there, and they've got very aggressive M&A strategies to go and, fill the gaps. I'd do the same if I worked in the big boys. I get that, but the tokens aren't free. Money has changed hands at one point, and if you direct some of those tokens towards a certain SPH tool or whatever, you are paying for it directly. It is coming out of budgets within the business. So I think one of the things that we try and say is, regardless of that, let's say, budget having already been committed, even on top of that budget being committed, and you spend additional budget for something like a Particleworks, where we believe, to our core, let's get emotional, it's the right project. Fundamentally, you're going to get massive efficiency gains in terms of your ability to iterate. So there is a direct engineering time cost save, let's say a couple of months. That saves money. That's real cost save to the business. There's functional performance gains because you can run faster and iterate faster, particularly when you are striving for very aggressive functional targets. It's more likely going to be able to meet them on time to budget right first time. And that's a really important point, because if we reflect on where emissions legislation is going, it's ever stricter. Internal combustion engines are the dirty word, aren't they? EV is the panacea, even though we all know from a well-to-wheel point of view, it's ludicrous, saying they're sort of zero emissions. But there's also the physical testing point of view. Anything you can do to remove one testing phase, typically, is a massive cost save, isn't it? So what do we normally so bringing that together, David, with these kind of tools, when do we think clients are getting payback? Is it one program? Is it 2 programs? What's your feel? Or are you thinking right now, why are you asking this question, Alex? Do you know the answer to
that? I think you're definitely better suited than I am to answer that. But I mean, I think it's dependent on the size of the company, isn't it? Some of these companies will be spending hundreds of £1,000s on a single testing loop. If we can remove that, well, you've paid for 2 years right off the get-go. Some of the smaller companies, obviously their testing loops are a lot cheaper, but still we're usually seeing a return on investment within a year, if not faster. Yeah, as you say, for a lot of the big OEMs, it's often within a single program.
Yeah. Okay. So my other question that popped into my head while we've been chatting is that of DEM, DEM. So I've sowed the seed there, David. What is DEM? Why does it matter for something like piston cooling, oil in engines? Why would I throw that comment in there specifically? Because clearly I'm loaded and being facetious at my intent. So let's talk about DEM. Yeah,
so DEM is the discrete element method. So this is another particle-based solver, but we're solving for solids using DEM. So dust, powders, anything at all that we can simulate as particles. And rather than solving the Navier-Stokes equation for the fluid flow, we're solving Newton's equations of motion. Where that is beneficial to Particleworks is that we have an add-on within Particleworks called GranuleWorks, which is a fully integrated add-on and allows us to do fluid and DEM, or well, we can do DEM alone or fluid and DEM simulations at the same time. As far as we're aware, this is the only tool on the market which can do particles for both the solids and the fluids within the same suite. So we can do there are other DEM packages out there that can couple with traditional solvers, but in situations where we have a free surface or splashing, as we've already discussed, those traditional solvers are not really very appropriate for that application. So in cases where you have solid particles with fluid splashing, well, Particleworks coupled with Granulworks is really the only application out there that can solve that problem. So within the internal combustion engines, often there's a sediment or bits of metal shavings potentially within an engine, maybe an older engine, and you want to be able to analyze that and see where they're going, and maybe design some kind of baffles to try to keep them into a certain area so they can be collected easily. That's something that we can simulate and have simulated using Granulworks coupled with Particleworks.
So to hit that home, because I don't think that's a really important point. So going back to my loaded question, because and particularly for off-highway or agricultural customers, or let's say OEMs that have product lines maybe in let's say, I don't even know what the politically correct way of saying it is, not first world or Western countries, whatever, where you've got much more disparate road surfaces. Maybe that's a good way to put it. Much more kind of off-road or gravel, where there's a high rate of, let's say, dust ingress or whatever. I'm going off track here. Get back on track, Alex. Anything you can do to understand, let's say, abuse load cases or reasonable standard deviations or the extremes of an oil quality within an engine, if you can account for as wide a oil quality as possible, or let's say your most aggressive or abusive customer in terms of how they use the product, they've missed oil changes, they don't put the right grades in or whatever, or I'm sure we can come up with a load of scenarios. If you can keep the engine operating at that functional performance requirement, fuel efficiency, emissions, or whatever, that's going to be able to help you push that service interval timeline as far down the road as possible. So if you're you've got a big fleet of these kind of vehicles, fundamentally you're going to keep your on-time your on-time availability of the product. That's real money and real revenue, real cost save to the business. That's a kind of hypothesis. Do we think we're picking that vibe up from customers, clients, that's actually a really good point for this tool? Because fundamentally you cannot simulate that in other tools.
Yeah,
period.
Precisely.
Okay, there we go. There's your hook. There's another hook, Cameron. You can have that. Put that at the front. Okay, cool. All right, so I'm probably running out of puff then, David. So what we meant to do with these things, I meant to thank the guest. Right, so thank you, David. You're the first guest on the podcast, which is good. So I think this has gone vaguely well. Thank you to everyone, obviously, in the audience that's watching. We really appreciate it. We're trying to sort of share some of our knowledge, share some best practice. We'd love it if you also comment, get involved, ping us a message, send us an email. I'm Alex Redman. David Percival, you can send us an email. What's my email? a.redman@enginsoft.com. What's yours, David? Or you don't want to share it because you get bombarded?
d.percival@enginsoft.com.
Cool. You can hit us up on LinkedIn as well. Just ping us a message, write something in the comments, like, share, subscribe, all that kind of stuff. Hit all the buttons. I sound like a right influencer. This is horrendous, isn't it? We've also got the website. We have a specific Particleworks microsite as well. What's the email address of that, David?
I believe that's particleworks.co.uk, or it might be .com.
Oh, yeah, I think it's .co.uk, I think. But yeah, feel free to take a look at that. Yeah, we've got social media, and I think, David, we've got a webinar coming up soon, although by the time this comes out, it will probably be old. So I won't say the date. I'll just say we always have webinars coming up on a number of topics. Feel free to join some of those. So thank you, David. Let's leave it there. It's been great talking to you. Thank you for taking us to the Pareto Front.
Thank you very much for having me.
See what I did? All right. Good man. Cheers, buddy. Appreciate it.
Cheers.
Bye-bye. Bye-bye.